Okay, talking about waves. You might wonder, well, okay, we talked about a wave going through some material medium, unless it's light. And we said that the medium oscillates, but if this is a string, this piece of string just goes up and down. It doesn't travel, it doesn't translate. What's the difference between a wave and something that's moving through space? So if we talk about particles, and this does hint at some quantum mechanic question, you might have heard of wave-particle duality for electrons and for light, and some interesting things there that we have to think and rethink. But this begins this idea. Particles, objects, things that we've been doing in this class. If our blue block, B, is approaching our red apple, A, and they're going to collide, they collide and they, have some interaction there, right? And anything could happen. B could keep going forward or whatever, but say they bounce off. Anyway, B doesn't go through A, does it? Unless it breaks through the apple. So particles think they bounce, right? That's the kind of the basic principle here, is that they bounce. All right, waves are different because it's the disturbance that travels, not the medium. If I go over here, we're going to have this rather than bouncing collision, we're going to have interference. Interference is a key phenomena of waves that we use and measure, and has lots of great history, but I won't go into it now. Let's keep it simple. So I'm going to have perfect constructive interference. I call it CI, I could call it PCI, but let's keep it perfect constructive interference. And then I'm going to look at destructive interference. And this only happens with waves, so let me show you what it is. So B is coming in, it's one of those little wave pulses on a string or something, you can think of it that way. And A is going to come in as well, and somehow make it just the same shape and amplitude. And A is traveling in like that. Now what happens when they overlap? Well, think of a water wave. When two water waves come together, and the crests come together, you get a taller wave, right? So blue plus red color gives us purple color. So there's A plus B in constructive interference, right? Now think about a spring too. When it's fully stretched or compressed, it stops. But it doesn't mean it doesn't have energy, right? It stops, the velocity is zero, but it's changing. Right? And so too, what happens here is that B just keeps on going. That bump B, A didn't bounce off. B just kept on going through it, that disturbance. So we think of it as an existence on its own, even though it really isn't. And A keeps, that's different than bouncing off. And that's called interference. And that particular, right here, I call it constructive interference, or CI, just too many letters. Now what happens if B comes in, and you got your blue bump coming in, and I have a perfectly mirrored bump on the bottom, A, and it's coming in. And they're traveling along, and blue says, go up, and A says, go down. So they go, there's some tension in there, so it's not just going to stop and stay stopped, just like at the end of a spring oscillation. And so when I get the two together, I get red and blue is purple, so I get destructive interference. A plus B is nothing for that instant, for that moment. Okay? This is really amazingly useful in all of science and technology. And what do we get out the other side? Well, this shows you that in fact it is A. Good old A is heading out the other way, and B just keeps on going. So they just stop, have a coffee, and then just keep on going. Right? That's very different than bouncing. So that's a good place to start with a fundamental difference between this phenomena, particle phenomena, and wave. And when you describe things with a particle phenomena mathematically, you might get one result mathematically, prediction. You get a different prediction with waves mathematically. And then you do the experiment, because what is. It does get a little fun and interesting when you get to quantum mechanics, but that's later. So, okay, that's the essence of the difference here. Let's go over here and talk about thinking about waves now, continuing to think about waves. We said it's an oscillation plus a translation. If you oscillate and you translate, you have an emergent property of a wavelength. A wave comes out of it. Well, it's oscillating and translating. So this piece oscillates that piece, and so on, the disturbance. Let's look at some basic kinematics. We'll hear in a second. Let's first check the units. So frequency is cycles per second, called what? Hertz. Because you know more frequency has more energy, so more frequency hertz. More. So velocity is in some length or distance unit, whatever you want, miles, inches, nanometers, whatever you want, but we'll go with meters per second. And the wavelength is just the length of one bump. So that would be, if I'm using meters, you can also use nanometers, meters per cycle. Now that's really going to help you to keep that cycle in there. All right, so what I want you to do, if you want to pause, try to write the relationship between those three variables. So pause and struggle with it a little bit. That'll help you. Even if you don't get it, the struggling will get you ready to get it. Okay, now let's go back to basic kinematics. So basic kinematics will really guide us here. You know, delta x, how is that related to the velocity and time? Well, let's see, meters are equal to meters per second times second. And if it's a constant velocity, that's it. You don't have the 1/2 AT squared stuff. All right, great. Or you can rearrange that. So once you have that, this is not three equations, right? You know, the units get meters, meter per second, times second. It all works. This you could write as this, right? Or delta t is equal to delta x times meters over meter per second, the seconds. That should all make sense. So you know that. So this shouldn't be a mystery to you. We're going to have to see, you have to be careful with this though. Now if you divide everything by cycle, what's a meter per cycle? What is it? Lambda. It's the wavelength, right? So you divide that by cycle and you get lambda of your wave. This is meters per cycle is equal to, let's divide V. Well, we don't, because that's a translation. It's not the oscillation. That's the translation part. So whatever. That's just V. That's the V of the wave, or the translation. Now we're talking about is the V of the wave. Right, that's fine. That's meters per second. What's the time for the oscillation? What's the time for one oscillation called? The period for the oscillation, right? So that works, because this is the seconds per cycle, isn't it? Meters per cycle equals meters per cycle. It's the same equation, isn't it? Now you can put it in terms of period, but could you put it in terms of frequency? Sure. Period is what? It's 1 over the frequency, right, of oscillation. That would still give me seconds, better give me the right units. Right. So you can get that. You don't have to memorize it. It's nothing new. It's just per cycle. And you use it so many different ways. You throw it all around. Just if you start there, you can rearrange it however you want. What other equation do I have? V is equal to lambda f. Check the units. Meters per second is meters per cycle, cycle per second. Cool. And just, the more you use it, you write it without even thinking. But for now, as you learn it, just kind of pause and, you know, start here, divide by cycle, and the more you do it, the faster you get. So you have to log in your time. I got lambda equals, I got V equals, what's F equal to? V over lambda. I can't remember all those unless I've been using them just regularly, doing lots of homework, getting all loaded up for that exam. But I can always go back here and take 10, 15 seconds, maybe 30 seconds most to go here, turn it into this. So we've got now this equation. Now there's a reason why I think, now plenty of books and sources write that as your equation. It's fine if you understand it, but be careful, because this equation says, hey, if I double the wavelength, the speed then would double. Mathematically, that's true, but we're talking physics. So math is broad, it's brilliant, it's wonderful. Physics restricts the math to physical phenomena, to what we're talking about. And so what I just said didn't make any sense. So if you really want to keep the sense of it, you'd start here, the lambda of the wave. You see, that's meters per cycle, meters. Without doing all that meters, I need meters on top. Well, I know velocity has meters, right? Meters per second. I got to get rid of the second, so I multiply times time. Or if you want, divide by frequency. So this is a little slick and probably too fast for you to just doing it, but there's the speed of the wave. And I highly recommend writing it that way, and I'll show you why. Let's go. What causes what to happen? Physically, what determines the wave speed? What determines the oscillation frequency? What determines the wavelength? I'll tell you, the wavelength is determined by this. Speed, wave speed, and wavelength is also determined by the frequency of oscillation. Let's see it. You can do this on paper, and then you can do it with physical waves and demonstrate it. Let's go over here. I'm going to show you two cases. You have to think physically. Okay, we got this wave. We know all about that guy. All right, so let's do it this way. Let's keep, it doesn't matter, let's keep the same frequency of oscillation. I got my colors right, okay, good. And vary the v of the wave. Okay. So I want to go slow and then fast. But I got to keep the oscillation the same. Okay, the oscillation frequency the same. So let's draw that wave and see what happens. That means that I've got to go up and down the same, but I go slow, and then I go fast. What happens to the wavelength? Where is it longer? Where is it shorter? I go slow. If I go slow, then in the time that I go up and down, I haven't gone very far, have I? But if I go fast, in the time that I go up and down, I go far. So you can do it here. You got it. It's like rubbing your head and patting your stomach, or patting your head and rubbing your stomach. You got to do two separate things. This is really it's deeper than it seems. It seems simple. So I'm going to oscillate up and down at the same frequency. And then I'm going to travel. I'm going to travel slow. And then I'm going to travel fast. Trying to keep the frequency the same. So what can you tell me about the wavelength here? It's a short wavelength, right? And what about here? It's a long wavelength. So if my frequency stays the same, but my speed changes, that's going to change the wavelength. The wavelength depends on the speed. In what way? Well, in the following way. Wavelength goes like, what is it? Does it go like the speed, or does it go like 1 over the speed? If the speed gets more, does the wavelength get more or less? More. So it can't go like 1 over, it's got to be like that. And we know the units are such that it's to the first power. All right, cool. So I've shown that wavelength goes like the v of the wave. Now let's do the opposite. Okay, so let's vary the frequency of oscillation and keep the speed the same, which is very common. This is often what we do. But you know, this actually happens as you go through, as light goes through water, as light goes through glass. And this is often not understood. I'll give it to you as a hint right now, and you could do it when you do oscillations, optics again. The frequency of the light stays the same. It just can, as it goes this way, through water or through glass, it'll slow down. The frequency will stay the same though. So now I want to do the same speed. Okay. Same v wave. But I want to oscillate with a slow or low frequency, low rate of oscillation, low frequency and a high frequency, and let's see what happens. So that's what I'm going to change here. I got to go at the same speed, so I'm going to go same speed, right, as best I can, and see what I get. If I get a low frequency, I'm going to go up and down slow. Low frequency. If I get a high frequency, what happened to the wavelength? You can see it. You can draw this. You get to bring your pens to class in your brain. So you see a long wavelength and you see a short wavelength. So that means that the wavelength goes like the frequency or 1 over the frequency. Higher frequency, shorter wavelength. This can't be true. And so this gives you a deep physical understanding of that equation that we just derived from delta x equals vt. Right? Or lambda equals velocity times the period, or lambda equals velocity divided by the frequency. It's just, don't see this as all kinds of, don't try to memorize the symbols. You know, if you start here, you're there, you got it. But you should also develop a physical intuition. And that, you know, if you do this, you've got it. But do it, you've got to do it 5 times till you own anything. Okay, cool. So that's that. So the next question finally is that we're exploring the simplest of equations. It's hard to imagine a simpler equation than this, and yet the physics is rich. Fine. The wavelength is determined by the velocity and by the frequency in this way. So I'm going to write that this is determined by v wave and the frequency of the oscillation, which is called the frequency of the wave. That's what determines that. So you can't just say, I'm going to change that and then change that. This doesn't affect the velocity. It goes the other way around. So v wave, what determines the v wave? We're going to explore this more very shortly. The v wave is determined by properties of the medium. What it goes through. As light goes through glass, it slows down. But you can think of that as a particle description of light as well, and that gets interesting. So this is deeper than it may appear. What determines the frequency? This is determined by the frequency of an oscillating source. The oscillating source determines the frequency. So let me show you that. Okay. good stuff here. That's important to realize. Well, so I can change the wave speed by changing the medium I'm going through. If I increase the speed, I'll go farther every cycle. If I decrease the speed, I won't go as far every cycle. If I oscillate faster, well, that's going to shorten the wavelength because I'm going to oscillate really fast. It won't go very far before I get back. If I oscillate slowly, then I'm going to go farther for every cycle. It really makes sense, but take the time to get the physics because the math is easy, but it's very dangerous. Right? You can't go up here and say, oh, let me see, if I double the wavelength, I double the velocity. That physically is not true. Right? If I double the frequency, I double the velocity. In fact, light, a rainbow through a prism, as it goes through a prism, the different colors, the different frequencies, travel at slightly different speeds in a prism. That's why they fan out. You learn that in optics. Different colors have different frequencies. Okay. They do travel at different speeds. So there's something that goes on there that's interesting in that interaction. Something interesting. One particular frequency, when it goes through, will slow down as it goes through, say, glass. So the frequency will go through there, and it does slow. So something interesting that goes on there. We'll get to that later, right? But for a basic wave understanding right now, just think of it as we drew it up here. Hey, if you can make the wave go faster, it's going to have a longer thing. If it goes slower, it's going to be shorter, and so on. So let's show that. Two ways. Sound and this wave machine thingy. Strings work great too, and you can explore that. You can understand musical instrument design. There's definitely an art to that, as well as a science. Okay, so here's the source, right? You need an oscillating source to make a wave, and then it's got to be carried along from one particle of the medium to another. So I can oscillate slowly. My oscillating source will determine the rate at which the medium oscillates. The speed is determined by the connection here, the medium. I can oscillate with a high frequency, and then the wave has a high frequency. I can oscillate with a low frequency, and the wave has a low frequency. So I am the oscillating source, and I determine the frequency. If I if I have a low frequency, the wavelength is long. If I have a high frequency, the wavelength is short. Because I'm going up and down fast, I can't go very far before I complete a cycle. Does that make sense? You guys cool with that? It's okay. Okay, how else can I change the frequency? We're going to get into this. Kind of cool. Let's go over here. Oh, remember our oscillations, rotational inertia, moment of inertia. I can hit this guy. Seeing that it's kind of a higher frequency than if I slow down the rate of oscillation by increasing the rotational inertia, because this thing is the oscillating source. It makes the air oscillate. This piece of air doesn't get to my ear or the camera. This piece of air, it oscillates the next piece, just like that. If I increase the rotational inertia, it's going to slow down the vibration, the oscillation rate. Frequency goes down. The oscillation of the fork here goes down. The oscillation rate of the air wave goes down, sound wave. And I experience that as some pitch, sound. Right? Color is an experience, some weird old thing going on here, which is a lot of fun, right? So you can change the frequency of the oscillating source, and that'll change the frequency of the wave, and if you change the frequency of the wave, that'll change the wavelength. Let's look. So this one's kind of easy. It's just there's an oscillating source that makes a wave. Right? Just that. High frequency, low frequency. This one's a little more interesting, and we're going to get into that now. And in particular, as I said, Light will slow down going through water or glass. It has different speeds. So there's some more deep things. A really nice example here is waves on a string, because you can pull them tighter. So we're going to explore that. And that'll give you a good sense. And we can talk about air. The fact that the speed of sound is actually different. It depends on, you could imagine, the density of the air, the temperature of the air, the water content of the air, things like that. So the pressure of the air, how much is compacted. So those things determine the wave speed of sound going through air.